writing. So the basic theory is the resolution is proportional to the wavelength and 1 over the numerical aperture. And there is a constant that we call K1. And then you ask yourself, if I need a special resolution, and I know lambda, what is the numerical aperture that I need? So if I work on a 32 nanometer technology, and I work with a 193 nanometer technology, which is the standard technology today, and K1 we take 0.3, then I need a numerical aperture of 1.81, which is very, very high and almost impossible to get. If I want to work with 193 nanometer, for example, give me an approach. If I ask you, I want to work with 193 nanometer and get 32 nanometer technology, and I cannot get this numerical aperture, what should I do? Immersion or double lithography, double patterning. If I want to go to 157 nanometer, then numerical aperture that I need is 1.47. It's high, but it's almost achievable. And if I work with a 13.5 nanometer technology, I need a very low numerical aperture, so it's less of a problem. So EUV is a system which is working with a 13.5 nanometer, or more accurately, around 13.4. And this is the micro exposure tool. And just I don't have a full image of all the tools, but I took from the literature some tools that people put in the web, and I copied it and I put it in the lectures. For example, this specific tool, this is the beam, and this is the reflector, and this is the mask. And the mask is imaged here on the wafer. So the light is coming like this, illuminating the mask, and the image is hitting these two reflectors, back to these reflectors, and back here. So as you can imagine, in this system, for example, you need to scan the mask and scan the wafer to get the image. Numerical aperture is 0.3, resolution is 30 nanometer, but the field is very small. Field is the area where you do the actual exposure. So in this specific system, the field is 0.2 by 0.6 millimeters square, and the magnification is 5x. This is an artist's sketch of an EUV tool, and I'm bringing it to you just to show you the size of the tool. And I've seen some of these tools, they are pretty big. This is a camera, but it's not exactly what you call a portable camera. This is a big camera. And one of the reasons is you need a big source for the EUV. You need a high intensity source for the EUV. This is another EUV exposure tool. And you have the main tool of the chamber. Now if you look at the chamber of an EUV tool, it reminds you of a vacuum system. And this is exactly what you have there. It's a high vacuum system where you generate this. You have this EUV source, and this specific source is called a Z-pinch xenon discharge, 35 watts over 2 pi degrees. And I'm going to show you immediately in the next slide, in the next few slides, what does it mean, a Z-pinch source. Z-pinch source is a special source, which I'm going to describe the details in a minute. But look at the values. This source can generate 35 watts of energy over 2 pi. And here you have all this wafer holder and all the system. So what is a Z-pinch system? The basic idea to generate extreme ultraviolet is based on technologies that were developed. Yes? It's 32 watts over 2 pi, which means the light, okay, let me explain it to you. You are emitting 35 watts, and the intensity is distributed over 2 pi degrees.
It's 2 pi in spatial
4 pi is a complete sphere, and 2 pi is half sphere. This specific source, you see the light, or at least the sketch of the light, it's emitting, and the light is emitted from here to here, and it's approximately 2 pi. Actually, in this specific system, it's slightly less than 2 pi. The idea of this EUV source, or gas discharge source, is to take a gas and confine it to a very small area and generate a strong, and apply a strong electric field. So you have a deionization unit, is a source where you take, in this specific case, you take xenon. This is the working gas. And you apply a strong electric field. You apply strong electric field between the blue and the red electrodes, and another electric field between the source and the chamber. So you apply the gas, apply a strong electric field to ionize it, and then the gas is flowing. And here you apply another electric field, which is extremely strong electric field. You generate arc, basically the gas is exploding. You apply a large amount of energy through a very small volume of gas, so the gas is exploding. And the system is a little bit more complicated, because you use some magnetic fields or other fields to confine the gas to a very small point. We call it a Z point, or a pinch point, where the gas is flowing to a very small amount. You apply a strong electric field, and the gas is exploding and generates very high intensity ultraviolet light. Typical input energy is 5 to 40 joule per pulse. The pulses are very, very short. The spectrum of a xenon discharge, is about this. This is the shape of the spectrum, and there's a very high intensity, around 13.5. This is one type of source. Second type of source is a laser-produced plasma source. Instead of using very, very strong electric field, you use very, very strong lasers illuminating a very small volume of the gas. So you take a huge laser, and you focus it on a very, very small area. And you take a high-intensity laser and focus the light to a very, very small volume. So you hit the gas, and the gas practically explodes. And when the gas explodes, it generates extreme ultraviolet radiation, and this is called laser-produced plasma source.
What does it mean, explodes?
Explodes. When you take, imagine that you take, let's say there's a gas in this area, and for a very, very small point, you apply a huge amount of energy. So the gas heats up, and all the electrons are going to some levels. But since you heat it so fast, there is no heat transfer between this area and the rest. So the gas practically expands enormously. It's like a shock wave. And this is practically an explosion because of the extreme high energy which is localized in a very, very small volume. You can think that the rest of the gas is cold, and only a small point of the charge is extremely hot. So this point expands in a very high speed. This is what you call an explosion.
The creation of the photons?
Because you take a matter and you heat it to extreme temperatures. So the electrons are going up, and when it explodes, they go down. And it happens that in xenon, most of the emission is at about, by the way, if you look at the emission, you see the emission is, sorry?
Around 11, there is another.
Actually, there's another peak at 11. These are basically, the electrons are going, there are few electron levels in the gas, and because of the high temperature, some of them are excited, and then they go down to a lower level, and they emit the energy. Now, you need a very high energy because you know, typical, or if you go to noble gas like krypton, xenon, neon, and you excite electrons to high level and they go down, then you have emission in the visible, which is yellow or green. So you would like to have a lot of emissions between not the valence electrons or the outer shell electrons, but electrons in lower energy levels, which are much more energetic. And or you have a large delta E between this energy, between the shells. So I don't remember the exact transition, but you need to invest a lot of energy to move electrons. So when they collapse, when they go back a large delta E, and then you have emission in the UV. Now it's kind of explosion in the sense that when you have a gas expanding at a very high speed, this is what you call an explosion. So you have the source, you collect the light and in a field stop. This is called a quasi-critical design. The source is imaged into the field plane. So you use some optics, you shape the beam using some lens, and you got here as an image, and basically this is one typical of exposure system. When you have extreme UV, when you want to illuminate with ultraviolet, extreme ultraviolet, you need some optical systems. So this is an example for one optical system. This is another EUV system. Unlike the previous one, which was a artist sketch, this is a real system with a real person, and this is how it looks. And the reason you have this big stainless steel container is that you need to have a vacuum system, because at this wavelength there is a significant absorption in the gas. So you need to have, and also you can ionize the gas. So you need to work in vacuum. It's another EUV system. And the EUV technology basically today can be broken into two major decisions today. First, should we use, and as we speak, there are some discussion now which direction to go. Is it going to use discharge-produced plasma or laser-produced plasma? Also, most common sources today use xenon, but you can see other sources with tin, indium, and lithium in a gas form. So you have to first evaporate it or vaporize it. Very easy to evaporate tin and indium. Their melting point is like in few hundred degrees Celsius. And then you heat them, you generate gas of the metal, and then you can irradiate it and get plasma source. By the way, the story is, and I still have to check the facts, but the story is that this technology was developed as part of the Star Wars technology. They developed very strong X-ray sources. They want to move up to satellites to illuminate other satellites, to basically kill their electronics and to neutralize them. So this is some of the benefits of the Star Wars technology. I have to check this story if this is correct, but it's a nice story anyway. Comments?
How does the so high energy photons won't corrupt the photoresistant silicon itself?
They will not corrupt. Actually, the silicon is almost transparent at this wavelength. The absorption of the silicon is not so high because silicon is it's not so heavy. And you need to design an ultraviolet sensitive photoresist that will not be corrupted. You're absolutely right. If I will use the wrong materials, this X-ray will corrupt it, or we get some damage. It will be damaged. But there are some ultraviolet sensitive or X-ray sensitive polymers which are sensitive to this wavelength without damage.
And another question regarding vacuum. So every time wafer is introduced to the system,
Yes, it might be a little problem of throughput. So you have to, but you can solve it by building transition chambers and load locks and yes. So it's just makes the system more expensive. I don't know exactly the price of such system, but it's in the range between $50 to $100 million per unit. So they are not cheap.
and the safety for the
It's the same rules as operating with an X-ray system, I believe, but it's a soft X-ray, but there are some rules, same as you go to your dentist, there are rules. You have to move in a certain places and don't go to certain places. It's manageable, but you need to know what you're doing. You don't want to be irradiated on a daily basis. And by the way, the alternative that for many, many years people thought it will be the good way is to use X-ray lithography, real X-ray. It's much shorter wavelength. It's in the range of 1 angstrom, 0.1 nanometer. It's a really high energy photons and very, very high resolution potentially. And this technology was believed to be very promising. It's a lot of effort and money was invested on it. However, it didn't work so well because the main problem was mask. So it's a very short wavelength, so you can get potentially very high resolution. And you can expose very large areas because you can generate very large beams of X-ray. So it's very easy to generate X-ray over a large area. If you go to the hospital or to lab to take like a chest, you can generate a beam almost the size of a human person. So it's not a big problem to generate a wide area beam of X-ray. But the main problem of X-ray was the mask. Because X-ray, the X-ray optics is not capable of, you cannot bring, sorry, let me rephrase it. You cannot build an optics to get a reduction of the image. So if you are designing a 22 nanometer technology, the patterns on the mask should be also 22 nanometer. So there was a big problem of high defect density on the mask. And this problem basically killed this technology for VLSI. However, this tool, and to generate X-ray is extremely simple. You take a piece of metal, it's called the X-ray target, you hit it with electrons, and then you have X-ray emission. You put here a window. Typically, the window is made of a material with a low atomic weight, like beryllium or carbon, because there is low absorption. And then this is beryllium window. And then you have the X-ray coming. You keep this ambient in helium, so it's clean. And you put here the mask, and you put here the wafer, and this system exists. There are some applications which is very, very useful. It is not so useful for high resolution because of the mask. But there are some other applications which is very, very useful because X-ray is a very energetic beam. So when X-ray penetrating the polymer, or the light-sensitive material, it can travel very, very long distance. So there are applications where you need to do lithography with a very thick resist, 50, 100, or 200 microns. Now these resists there is a very famous process called LIGA, L-I-G-A, which is a process used for MEMS, for micro-electromechanical system. And this process needs a very thick photoresist. So you can use X-ray to produce micro-mechanical structures. Some technologies, some processes using X-ray exposure system, but this is it. The second or the third technology is the electron beam lithography. Now, electron beam lithography is the working horse technology for nanotechnology. Because with electron beam lithography, you can print very narrow lines. In the system that we have here in the university, we can print easily 15 nanometer lines. And if you try very hard, I can show you even how to print better. And this is let's say 20 or 25 years ago, people already used E-beam for nanostructuring. or nano-lithography. So direct write e-beam lithography, where you take an electron beam and with the tip of the beam you write whatever you like. It's like writing with a pencil on a board. And with electron beam lithography you can get high resolution and wonderful lithography, and then you ask why this is not used in the industry. So let's do some exercise of simple mathematics. Let's say we want to print a pixel, and each pixel is 30 nanometer by 30 nanometer. 30 nanometer, to remind you, is 3 times 10 to the minus 6 of a centimeter. So how many pixels we have per centimeter? 3 times 10 to the minus 6, 3 to the 10 to the minus 6 is 9 10 to the minus 12. 1 over it is 1.1 10 to the 11. So for every centimeter square, we have about 10 to the 11 pixels. So let's say I have a machine that generates electron beam, and I illuminate 1 pixel, 2nd pixel, 3rd pixel, and I need some computer to control, yes, no, I illuminate, I need to control the beam. I can want to write here and not to write here. So let's say I have a very good system. I can modulate it at 1 gigahertz. So I can modulate a 10 to the 9 pixel per second. And 1 gigahertz modulation, it's high. It's a high speed for such system. So how many pixels I can print per second? How long it takes to print 1 centimeter square? 100 seconds, right? If you take if I have 10 to 11 pixels, and I can write 10 to the 9 per second, so it's 100 seconds. How many pixels we have on a wafer? The wafer today diameter is 300 millimeters. So the area is pi r square is 15 square, it's 225 times 3, it's 700 something. Let's take 700. I have 700 centimeters square, and it takes me 100 seconds to print 1 centimeter square. It means it takes 70,000 seconds to print 1 wafer. And this is if I have an excellent tool without any overhead. How long is 70,000 seconds? It's 3 hours. How many hours? 20 hours. I think this is, if you have a machine that can print 1 wafer every 20 hours, and this machine costs $5 to $10 million, you will never see your money back. Because just on a $10 million tool, only the interest on the money is $2 million a year. And you sell every wafer today for like a few $1,000s. So it simply doesn't work. So electron beam lithography, because we write, every time we write with a single beam, it's an excellent tool for research, excellent tool for prototyping, but it's not a commercial tool. We like it very much in the university because we can do really amazing things. So how to produce a commercial tool? There are a few options. There are 2 major technologies which are being tested. One is called electron projection lithography. In electron projection lithography, you take a beam of electrons and you take a special mask, and this is you scan the mask, and here you design a projection lens. In this case is 1:4 magnification, which means you take the electrons and you apply electric field so they move like this. So you take your image and you reduce it, and if you design the electric fields, you can actually have a reduction by 1:4, and you build a kind of a circular electric fields which have a potential lines that the electrons are traveling in this trajectory. And what happens, the electron from here moves in this way, electrons from here move in this way, the electron in the center stays in the place, and this is equivalent to optics where the beam, in optic system, the beam is moving like this, and you focus the beam, and you get an image on the structure. So this is the wafer stage. You have the wafer, and this is a magnification of the center part. We have the electron source. The electron source will generate a wide beam. So we take a single source of electrons, and there are few ways to generate electrons. The best way, for example, is to take a metal and apply a strong electric field, and you get, basically this is called cold field emission. It's if you apply more than 10 to the 7 volt per centimeter, if you take some metals, and like a tungsten, for example, and you apply on the tungsten, on the metal, more than 10 to the 7 volt per centimeter, you are pulling the electrons out of the metal, and then you have an electron source. Another option is to heat the metal, so you have thermal emission of electrons. Or you can do both. You can do some thermal emission and field emission. This is called thermal field emission. This is your mask, and the beams is going through the mask, and here you put some projection lens. It's an electron beam lens. It's an electrostatic lens, and you focus it on the wafer. This is the EPL mask. This is how a mask looks like, and I present you the image of this mask. Now, this is how it actually looks, and the reason is that the electrons are absorbed in most materials. So the mask must be very, very thin. But because this is the mask itself here at the bottom, but you cannot make a large area which is very, very thin. So what's the mask actually look? People put some ribs to strengthen it. This is how it looks. This is the image of the 4-inch mask or 3-inch mask. And this is actually how it looks. This is a silicon. And how do you use basically a silicon wafer as the mask? Now, how do you etch silicon? You use a process called Bosch process, and I'm going to show you when we study about etching. We will study about deep silicon dry etching. The idea is that you take a silicon and you insert it into a system, and you apply a gas which is fluorine, F. But this fluorine is not in a normal state. You apply fluorine or fluorine compounds like CF3, which are excited, which are very energetic. So the fluorine reacts with silicon, and you're generating silicon tetrafluoride, which is a gas, and so the fluorine etches the silicon. So you etch the silicon, and then you take another gas, and this gas also containing fluorine, but also containing a lot of carbon, like what you have in your refrigerator. You know what you have in your refrigerator? Do you know the gas which you use in your refrigerator for cooling? Do you know the names of the gas? Freons. Usually freon. And what is a freon? Freon is a carbon fluorine gas. It's CF4, CHF3, C3F8. So this is basically, you can take a gas from your refrigerator which contains fluorine, and you excite it either by heating it or by apply electric field. So this gas contains fluorine, and fluorine etches silicon. Now, if you take this gas but operate it with a lot of hydrogen, you are generating a molecule of CHF something. And this C connects to an A, connect to a C, connect to a H, connect to a C, connect to a H, and we get a polymer which actually looks like Teflon. Do you know Teflon is it's a polymer which contains carbon and fluorine. So instead of etching, you get the position of this polymer, but it's very, very thin. Then you remove it on the bottom and etch again. And remove it on the bottom and etch again. So this is very similar if you want to drill a hole in a sand. If you want to drill a hole in the sand, you drill like half a meter, then you put a rim, like a piece of, like a tube. Then you drill another half a meter, then you coat the sidewall. So this technology is called the Bosch process or deep RIE, where you etch and deposit polymer. Etch and deposit polymer. And this is how it looks. This technique, basically, you can drill forever. Typical systems, you can drill a few hundred microns with very nice dimensions. So this is the EPL. This is actually made by Topan, published by Topan, and this is the mask. And this is how it looks. This is the wafer, and this is the exposed wafer. And now, because we now expose much larger areas, the speed of the exposure, the throughput, is much faster. And this is the 80 nanometer, 75 nanometer. This is the lithography, and this is the etching after lithography. So this is EPL, which is a very promising method, still under investigation. So if you ask me what are the technologies you will see in 10 years from now, it can be either EUV or EPL. Yes, questions?
You put a freon-based gas in the chamber and ignite it with the electron beam?
The etching, you ignite it by applying strong electric field. Just like that. Just put some AC field, few hundred volts, and you introduce breakdown. And once you introduce, it's like I will talk about it, I will discuss it when we describe plasma, but you see, you have it here. We have fluorescent lights in the room. What is a fluorescent light? You have mercury inside, it's mercury vapor. But if you so you apply here like 220 volts, and you apply 220 volts, you introduce some breakdown inside the mercury. But actually, you don't see the mercury light, because the mercury light is in the UV. This is why you coat the walls of the tube with fluorescent light, and you got the emission for the fluorescent. So this is an example that if you apply electric field on a gas, the gas emits photons.
So why do we need the electron projection? Or you can just do it with normal electric field?
Sorry, I missed.
Electron projection lithography steps in.
No, this is to make the mask. This process, sorry, I repeat. This is the mask making. This is how to make the mask for the EPL. Now, you make the mask, and the mask, the resolution, this is like 2 microns or 3 microns. And then you etch until you reach the bottom. You make and then on the top, the bottom here, you have a very thin silicon. You make your patterns on this thin silicon. This is the mask. This is not the mask. The mask is not here. This is thick silicon. The mask is here at the bottom. So you see, these are the rims, and the mask is here somewhere, here at the bottom. And this is, you don't see you see the mask is here at the bottom. You don't see the patterns of the mask because they are too small in this specific picture. But if you go to this area and magnify it, and this specific area is very large. As you can see it from here, it's 130 1,130 microns. So it's more than 1 millimeter by 1 millimeter. If you go inside and magnify it, this is what you see. You see the holes of the pattern.
The mask is made from silicon?
The mask is made of silicon. The mask is made of silicon, and you etch it to be like, it's like a chocolate. These are the rims, and you see at the bottom this very, very thin silicon. On this silicon, you make your mask. No. By the way, how do you make the mask? By e-beam lithography, by regular e-beam lithography. Because for making one mask, it's okay to work for 20 hours.
And the mask, the opaque part of the mask is...
This is the transparent part of the mask, and the rims are opaque. So the bottom is the mask, because this is X-ray. This silicon is very, very thin. Sorry. Oh, sorry. I should have thought. See, this is the mask is here, in this area. This is the rim. So this is the rim here. The mask is actually here. So you put your patterns on this part of the mask.
So how you differentiate between the opaque and the transparent?
You basically on your wafer, it doesn't show here, but this area is basically a dead area. This area you don't have patterns there.
No, but the question on the mask itself, when the electron goes through the mask, what blocks them?
You put some chromium, you put some metal which absorbs electrons, like heavy metals, or scatter them. You don't need so much to absorb, just to scatter them.
So you make this mask and then you coat it with metal and then you put it.
Then you coat it with some metal, and then you do the lithography on that. You can actually do you can do it first, and then do this etching process. But actually, I don't know which part you do first. Actually, questions?
I didn't understand why you need this grade.
Why do you need this?
Yeah.
Because it's impossible. This is very thin. This layer is few microns, and it's very difficult to have a piece of material which is 2 micron thin and very large area. This is just I don't have a structure here, but this is it's like a construction. This is like civil engineering. You want to keep the bottom, the very thin layers, so you build these ribs to keep it. Now, other lithography method. Now we go for nano-lithography. This is not for VLSI. This is for nanotechnology. And one of the interesting method is nano-printing, or sometimes you call it nano-imprinting. It's practically stamping. You make a stamp, and the way you make your stamp, you take silicon, and using e-beam lithography, for example, you put some lines of gold, and you produce it using some very clever e-beam lithography, because I told you with e-beam lithography you can produce very, very fine patterns. So you have one piece of silicon with gold wires, and this is your master. Then, sorry, this is okay. So you have these wires here. Now on these wires, I would like to print something. So imagine that you take a stamp, and this stamp you make from another polymer. Now how do you make the stamp? You take the negative, you take a piece of material which is the negative, and you produce it by e-beam lithography. And PDMS, or polydimethyl it's a polymer. By the way, it's very close to what you use in your house, what you call silicon rubber, that you use in your house for sealing. Silicon, but S-I-L-I-C-O-N-E. Not silicon, the element, but silicon with an E at the end, which is the polymer. So you take this, in a liquid form, you put it on your matrix and you peel it away, and then you have your structure. Then you can put like ink and print the red lines on your substrate. The substrate is silicon, and initially I did not explain well. Initially you take this is your silicon, and on the silicon you have gold, for example, and then you can print the red lines over the gold by stamping. It's like take your PDMS, put the ink on it, and stamp it. Now this can be ink, paint, but also can be a polymer which is a photoresist. This can be a biological compound. You can print structures using stamping. This is nano-imprinting, because these lines, you can make them in the nanoscale. So this is nano-imprinting, or also people call it soft lithography. Very common in nanotechnology because you can make this in the following way. You take your master, and basically this one is another PDNS. It's another. It's written here PDNS, which is another polymer. It might be an error in the slides because we use PDMS. Some people use, but this is a polymer. Maybe polydine. Okay, I have to figure out what is this polymer, but it's a polymer which is very easy to handle. And you take your master, this is your master, and you pour the polymer in a fluid form over your master. Then you let it dry. It's called curing. It becomes a rubbery solid. And then you peel it away, and this is what you get. Then imagine that you are now dipping your structure, but the PDNS stamp is inked in a solution which contains organic molecules which has affinity to gold. One of the most common compound is to use a compound which contains, let's say R will be some molecule, but has sulfur and hydrogen. This is called thiol, Thiol, thiol group. SH, the thiol group. And interesting, if you take a substrate made of gold, and you, sulfur, this molecule will make a very strong bond to gold. And you can actually design a molecule with a SH bond at the end and attach it to silicon, and this molecule you can, the R, and you can design here, you choose a molecule R, SH, and this R you can choose whatever you like. It can be a small molecule, big molecule, it's a molecule that later you connect it to another molecule. This can be a beginning to build a structure. So what happens is when you take this structure and you press it into silicon, this is an imaginary image, but this is what you get. You can get a self-assembled structure of your special ink on the gold. So this is the thiols form a self-assembly monolayers on the gold surface that reproduce the stamp pattern. So this is a way to print nanostructures, also to introduce self-assembled monolayers which are patterned on gold. And this is used for many applications in nanotechnology. Another very useful technology in the lab to build nanostructures is SPM. SPM is scanning probe microscopy. SPM is a method that you take a tip, you move it over your target, and then you can go up and down, and by the motion of the tip you can guess the shape of your substrate. You can use it for atomic force microscopy, scanning tunneling microscopy, and all this high-resolution microscopy. The general terminology is scanning probe microscopy because you scan with a probe. The probe can be magnetic, electrostatic, but if you are scanning, you can actually write. And for example, if you take the tip, and on the tip introduce your molecules that you want to write, you can actually, it's like writing with a pen. And this is called dip pen lithography. Dip in the sense, dip, D-I-P, which means to dip. Like, you know, dip for salads. So this is the same thing. So instead of writing with a dip of a salad, you write with this molecule, and it's a thiol molecules. You need, on the end of the tip, some drop of water to have some transfer media between your tip and your substrate. And what you do, This is a kind of a tip. The molecules travel down, and you actually can write a line with these molecules on the surface, and you can, the molecules, if you do it right, even the molecules here are random, and they will self-assemble here. This is a very nice nanostructure. And you can put a lot of, you can play games now. You can combine other materials, and you put a self-assembled monolayer. And you can write your name with it. You can write, they did it, but not with tiols. They did it with metals. But they did not use deep pen lithography. This is from Professor Chad Mirkin's group. Professor Chad Mirkin's group in Northwestern University in not far from Chicago. And it's a very famous work, which is a groundbreaking work on nano-lithography. The work that you mentioned by IBM was using scanning probe lithography, but not with organic molecules, but with metal molecules. The beauty of this technology is that you can write with a biological compound, with organic molecules, and you can later on connect to this molecule some other molecules, antibodies, proteins, DNA. It can be the beginning of some nanostructures which has some other use. So if I summarize it, optical lithography proven today for 22 nanometer. Some companies already have let's call it pre-manufacturing or manufacturing in advanced level just before commercialization of 22 nanometers. It's a very high throughput. Electron beam lithography, it's very promising. It has a very high resolution, but today with very slow throughput. So if you solve this problem, it will be very, very useful. Nano-lithography, sorry? You need electron beam resist. For every technology that I described, for optical lithography, you use optical resist. For E-beam lithography, you use E-beam resist. For X-ray lithography, you use X-ray resist. They are basically polymers which are sensitive to the specific wavelengths of the radiation. Now nano-lithography method, the deep pen lithography, is very promising. And actually, soft lithography is also used for nano-bio printing, and it's a very, very useful method. So this is the end of the lecture on lithography. Okay, ion implantation. So we learned how to do lithography. Now we need to learn how to do doping. Now what is ion implantation? It's a process which energetic charged atoms or molecules are directly introduced into the substrate. You use acceleration energies between 10 to 200 kilo-electron volt. Some tools today have energy of several mega-electron volts, and primarily used to add dopants, ions, into the surface of silicon wafers. And the goal is to introduce the desired species with a specific quantity, dose, into the required depth with a very lateral selectivity. Today is the dominant technology today for doping. It is very favored because first, you can introduce a large range of doses between 10 to the 11 to 10 to the 16th atoms per centimeter square. Another question. You have a wafer of silicon. How many atoms you have per centimeter cube? Approximately. 10 to the 23 is for 1 mole. 6 times 10 to the minus 3. But let's say if you have a centimeter cube, it's less than a mole. So 10 to the 22, 10 to the 23, 10 to the 22, approximately. How many atoms you have per unit area? If you have 10 to the 22 atoms per centimeter cube, how many atoms approximately? And let's assume a completely cubic structure. Forget this is diamond structure, forget HCP. How much? Why? 2/3, to the power of 2/3. So the question is that how many atoms we have per unit area? Something in the range between 10 to the 14 to 10 to the 15. So if I implant with a dose of 10 to the 16 atoms per centimeter square, which means I have more ions per unit area than atoms. If I implant with 10 to the 11, I have much, much less. Imagine like raindrops falling on the ground. The raindrops can fall in a very sparse, very large distance, or if it pours rain, then all the drops are falling one on top of another. Because we can control the dose, the amount of ions per centimeter square, very accurately, the dose control, which is about 1% or better than 1%, we can get very uniform doping of the silicon substrate. And one of the most important applications for ion implantation is the control of the threshold voltage of the device. You know, the threshold voltage of a device depends on the doping of the substrate. Because the threshold voltage of the device is the voltage when we introduce inversion. And the inversion occurs when the surface potential is equal to twice the Fermi energy. And the Fermi energy depends on the Fermi level, which depends on the doping. So the doping of the substrate determines threshold voltage. Now let's say that you produce, and you find out that you wanted 0.6 volt, and your manufacturer is point, and everything works fine, but for some random variations in the process, now instead of 0.6, you have 0.59. You have to, instead of redesigning the whole process, you say, okay, I can change a little bit the doping of the substrate. Or, if I have, you know, when you buy wafers, we always tell you, like in exams, we tell you, you have a wafer with 1 × 10⁻⁻16. But when you buy wafers from a vendor, when you buy wafers, the doping can vary because the manufacturer of the wafer have some random fluctuations. So how do you control the random doping of the substrate? The way to solve it, one way to do it, is by implant ions to control the threshold voltage. And everything switches at the same speed, no waiting for laggers. Another application. Some circuits today, you have on the same chip transistors with 1 V threshold, but other transistors with a different V threshold. And some companies can have, even on the same chip, 3 different thresholds. And the reason is, usually the current of the device is a function of the threshold voltage. The higher the threshold voltage, the lower is the current. Because the current, you remember, current is something times V gate minus V threshold. So when V threshold is high, the current is down. So if you want to save power, you operate with a high threshold voltage. If you want to accelerate, you want to work faster, you lower the threshold. When you design a system, sometimes you don't want all the transistors to be fast. So you can control the threshold voltage. So you can implant in different regions on the chip and get different threshold voltage. It's a low temperature process and a wide choice of masking materials. Now, an ion implanter looks like this. You have an ion source, and you generate a beam of ions, and they move until they reach a strong magnetic field. And you know that when an ion hits a magnetic field, it moves in a circular trajectory, and the radius of curvature depends on the ion, on the mass of the ion. So you put here an aperture which is very narrow, and you can move it and choose the ion that you like. Then you put here a bias of, if it's a positive ion, you put a negative bias of, can be a few 100,000 volts. You put another electrostatic field which makes the beam to move, to change the, if it's a positive ion, you put a negative bias, they're actually moving in this way. And the reason you do it, if some reason you have here some neutrals, and some contamination. The neutrals, if they are moving, they will not be affected by the electric field, and you put here a trap to catch them. Then you put here another, what's called XY scan plates. You put plates scanning in this direction and plates scanning in this direction, and it's like television. You can scan your substrate, and here you put your wafer. And the wafer is inside a metallic structure, and for example, you can measure the current hitting the wafer because of Kirchhoff's law. You know, the current going in is equal to the current going out. Kirchhoff's law is always correct. So if you just measure the current going out, or if this is a positive charge, it's actually electrons coming from here to neutralize the structure, you can know how many ions hit the surface. So it's very easy to control because we can measure current very accurately. So this is an ion implanter. Now the type of, let's go now, it's about 10-15 minutes on technology. How do you generate ions? You have an apparatus, for example, a very common apparatus is called a Nielsen source. You have a magnet here, and inside the magnet you have a piece of material, and inside you have a filament. So the gas is coming here, you heat the gas, and there is a very strong magnetic field here. Now when you heat the gas, you can ionize it. And you generate, like in a fluorescent lamp, you generate ions. Now you apply a magnetic field from the outside, and when the ion is moving inside magnetic field, it moves in like a cycloid structure. So there's a lot of collisions. And energetic ions hit the gas, generating more ions hitting the gas. So this way you generate a very rich plasma inside the chamber. And you put here, this is the extraction outlet, a very thin hole. If you put here a negative bias, some of the ions will go out. So this is a very typical source. This is the sketch of the previous source. Previous picture was a kind of more detailed structure. This is more of a sketch. For example, you take a BF3 gas, it goes through this filament, you heat it up, the magnetic field makes the structure richer, and what you have at the end, you can generate a boron if you take BF3, but you can also have, by the way, you can have boron BF3, you can have BF2+, you can have F+, you can have some species which are ionized. So what you do, you put here an aperture, and put here an extraction electrode, which is typically 30 to 50 kilo electron volts. And the ions are typically positive, because usually what they do, they lose one electron. This is a typical ion. And you extract, you get an ion beam coming out. The ion beam going from the source. And for example, if we take a boron, a BF3, BF3 is a very common gas that people use in the industry. And if you take a BF3, you can generate like boron. And by the way, boron has two isotopes. One is boron 10, second one is boron 11. They're slightly different mass. And also you can get, for example, also BF2+ with a mass of 49. So if you put a slit here, you can select, for example, only boron 11 to come out. And it's very typical that you choose only one isotope. So this isotope now, boron 11, going through your accelerator. Now, and this is a typical shape of an accelerator. Usually you don't accelerate with one bias, but with a series of electrons. Yes? Okay, now the question is, why only boron 11 came out? Because boron, you have a magnetic field, and when a particle moving in a magnetic field, you have a force perpendicular to it, so it moves like in a circle. So light elements, they move in a smaller circle. Heavy elements moving in a larger, with a circle with larger radius. So boron 10 is light. It moves in a shorter radius. Boron 11 is a little heavier, and boron BF249 is heavier. So boron 10 hits the wall, BF2 hits the wall, and here's an opening, and only boron 11 is coming out. So this is, by the way, do you remember the other name? Do you know the other name of such a system? It's a mass spectrometer. It's actually a mass spectrometer. People use it in mass spectroscopy. So you build a mass spectrometer inside the chamber. The main difference between a mass spectrometer for analysis, that this is a much bigger system which deals with a much higher density of beam, much denser beam. Now this boron plus hits basically hits what we call this is a linear accelerator. But if you see that the bias here, this is minus 59, minus 10, minus 15, minus 20, it's a relative potential, and this is called accelerator common. And what you see that we give a potential between each one of the rings, and we not always accelerate the same. And there's some, I don't want to go to details, but this is called electron optics, because if you think about this structure, between this beam and this beam, you have field lines, because this ring and this ring are in a different potential, so you have field lines. And the inside it's hollow, so the field lines are curved. And the electrons, when they are moving inside the field lines, they feel some force. So you can think about the electron beam is coming and being shaped through this structure. If you want to learn more, I can send you some reference about this system, this type of system, and this is called electrostatic lens system. What is the energy at the outlet? It's written here. It's 20. Because you accelerate to 59. Here you slow it down to minus 10. Here it accelerates to minus 15. Here it's this is minus 2. This is the potential, relative potential. And the relative energy here is minus 20. Is the last, as if it fills the last potential. And you can see that you initially accelerate and then you slow them down. And the reason you do it is because the beam is coming as a certain structure. And the beam is basically, you shape the beam, and each one between here and here, between this ring and this ring, the shape of the potential looks like not a sphere, but kind of a spheroid structure, so it acts like a lens. So you can analyze this structure, and I'm not giving you the detailed explanation, so you have to excuse me, but those are electrostatic lenses, and they operate like optical lens, and they basically take the beam and shape it to a focused and very parallel type beam. The beam of this 11, or Bohr 11 plus, moving and hitting these plates. Now you have few systems. One system that we had in the Technion, we had focusing and scanning electrodes on X direction and focusing in the Y direction, and the wafer was standing. Or the wafer is rotating. A very common system is the wafer is on a platen, on a big wheel. And this wheel can be huge, sometimes more than 2 meters high. And the wafer is rotating, and you illuminate and you scan only in X direction. And the reason to build this structure, so you can implant not one wafer at a time, but more wafer at a time, so you can get higher throughput of the system. You can implant more wafers per unit time. They are quite big systems. There are a few little things that I need some further explanation. First one is that when you implant a structure with ions, you can charge it. So one way to eliminate it is because a constant flux of positive ions on the wafer causes a buildup of charge. And the charge, once the wafer becomes charged, it repels other ions. So the solution is you create a constant stream of low energy electron, which you flow them. So you generate, near this target, you generate a flux of electron which neutralize the ions. assuming that your wafer is conducting. But what happens if your wafer has an oxide on top because you are in a step of the process that you have oxide on the top? So you cannot. Of course, if the wafer was conducting, I can just ground it. Yes?
The ions themselves in the beam, don't they reject themselves?
The question is whether the ions on the beam reject each other. The answer is yes. There is some interaction of ions in the beams. However, it's manageable. Of course, it limits the size of the spot. You cannot generate a very, very small spot, especially when you work with very high currents. You have to, what I can say, this is part of the design of the system.
Do you ionize the ions before they're implanted? With the gas?
You're ionizing it here in this ion source.
No, later. You said you put an electron beam.
To use electron beam to ionize the gas before? It's also possible.
No,
But
what happens? I mean, when do the ions deionize?
when you deionize them, you put electron beam, and you basically put here, excuse me, I run fast. You put here a flat gun, basically an electron gun which basically emits electron which reacts or recombine with the charge on the surface. It occurs on the surface of the wafer. Or other techniques, you put a grid which generates electron beam when the ions are almost as close to hit the surface. So this is called a neutralizer.
What's implanted is atoms, not ions.
Yes. We neutralize them just before they hit the silicon. So you can call it atom implanter, actually. But actually, in some systems, the ions hit the surface, charge the surface, and then the flat gun hits the surface and neutralize it. So you can either neutralize them before or neutralize them after.
The important part is to have the charge for acceleration.
Right. You need the charge for the acceleration. When they hit the surface, actually, it doesn't matter. You don't need the charge. This is the Faraday cup. Basically, if the ion beam hits the Faraday cup, you can measure the current. This is a very common method to measure current. Now, what the ion is doing when it hits the surface? Yes, question number.
Ions hit the surface or atoms?
If you neutralize it just before, then it atoms. Some system, I know that. It's a good question. I don't know if all the system now neutralize them before the hit or after they hit the surface. But it doesn't matter. It doesn't matter because once the ion hits the surface, it starts a series of effects which is the following. We call it ion implanter. We like to say that we implant ions, but you're right. We can neutralize it just before it hits the surface, or if it hits the surface, we can neutralize the substrate.
If it's neutralized by gas, how do you count current?
It's a good question. If I applied, you basically, it's a good point. If you say if I neutralize, so I have to put, let's say this system is good without neutralizing. If I want to neutralize it, I have to put the Faraday cup in a slightly different place. It's a good question. Now the following is as follows. Let's assume this is a wonderful crystal, and I shoot ions on top of it, and this is what I get. Because the ions are very energetic. It takes about 15 electron volts to break the bonds in the silicon. And I shoot a beam which is like 10,000 volts or 20,000 volts. So the ions hit the surface and basically destroy the crystal. So you can ask, what did we do? We spent so much money and effort to have such a wonderful crystal, and then we destroy it. But actually it's good. It's somehow, we can do the following, because we can take this structure, what we have here. This area is completely amorphous. If we implant for a long time, if we implant a very heavy dose, it will be completely amorphous, because we completely destroy the crystalline structure. So what we have here, it's an amorphous material with the silicon or the other semiconductor, and this black black circles or spheres, which is the dopant. Now I can take this structure, which is practically, this is amorphous silicon, which is a very bad semiconductor, and also doesn't conduct very well, and it's not so, we don't use it as is. But what happens if I will take this structure and heat it up? If I will heat it up, this will happen. It will rearrange itself. And the way it will rearrange itself is by a process which is called solid state epitaxy. Epi, you know what's epi? Like in a book, epilogue or epidermis. Epi is on top. And taxi, the taxus, it's growing with the same direction. So if I heat up the structure, what happens, this element, silicon, can move and come here. When it comes here, and it will make a bond with the silicon, I will gain some energy. So this is a favorable process. So I have one element coming here, and the interesting part, if one element will come here, I will have two bonds, one here and one here. So the elements would like to come here, and then to make a bond in a corner is a preferable process. So once I make, one neighbor comes here and makes this bond, then another one will come here. And then what will happen, I will build one layer of crystalline structure. Then another layer, and this process is called epitaxy. It starts to occur at about 500 degrees Celsius for silicon. As you increase the temperature, it occurs much faster. So you can do the annealing at 700 or 800 degrees, and then it takes a few seconds. And after annealing, what you have is a solid state material with the dopant inside the lattice structure. And if you remember from the course of semiconductor devices, when the dopant is in the lattice structure, it's a dopant. So this implantation annealing, the anneal repairs the crystal damage and allows the dopant to migrate into a substitutional site. When the dopant is exactly in the same site replacing a silicon atom, we call it a substitution. And when atom is in a substitution position, it's electrically active. For example, if I have a boron has 3 electrons in the valence band. So what it will do, it will take another electron from the structure and make these 4 bonds. But because it takes 1 electron from the silicon, it actually generates a hole. If this is a phosphorus ion, phosphorus has 5 electrons. So it will contribute 1 electron, so it will be N-type material. So this process is doping by electron implantation, and it's done by annealing. Now the situation is more complex, because as we implant, what happens, we can generate a set of recoils. The pink atoms is the ions that we shoot, and they hit this white atom, which is the target. And then we have one pink atom continue to move, but with a slightly lower energy. But we generate this green atom, actually this atom is moving to the side and can hit another white atom. So the green atom is a moving atom, and this is a target. So this can generate another 2 atoms. We can generate more atoms. So what happens, this pink atom, it will not move a single atom. It can move more than 1 atom. So this process of amorphization is what we call a cascade process. Cascade means is a process that has one step following a second step following another step. It's a process which we have few steps which occurring one after another. So cascades of recoil atoms. This shower of atoms, we call it also cascade of atoms. This shower of atoms moves, and this atomic cascade affects the crystal structure, and we have practically mixing of the atoms. The atoms start to move in a lot of unexpected positions, and we have everything is mixed together. Now one atom can generate a shower of few secondaries. This is called secondary atoms per collision. and the number of the collisions is proportional to the energy, because every collision, it loses delta E. So the number of collisions is approximately E over delta E we take 1/2 of it. So we can calculate the number of collisions. We also have electron cascades, because we also generate some electrons, and they can do some chemical changes. And the implanted atom, once the atom, the ion hits the surface, it's a one collision, second collision. After a few collisions, it slows down and then stops. Then a second atom comes. Then a third atom comes. So we have more and more atoms, and on average, they all stop in the same position. But you can have some variations because it's a statistical process. So we call this trajectory. This is it goes 1, 2, 3, 4, 5, and stops. We call this the total range, but we are not interested in the actual motion, but we are interested in the question we ask, how deep it is from the surface, because this is where we have the junction. So we are interested in the projected range, not in the total range. And the actual distribution, if we assume that we generate one atom, second atom, third atoms, and if all the processes were independent, you know that if you take statistical processes and you sum them again and again and again, it's like playing the game. You toss a series of coins and you find the statistic. Then run the game again. You know that the sum of many random events is, by the law of statistics, it's a Gaussian. If the events are independent, which they are not, but if they're independent, the profile of the doping should be Gaussian, which means this is the average, and we have some ions which stops before, some ions that stops later, but the profile, which is the sum of the game, should be a Gaussian. And if this is a Gaussian, we call Nx or Cx, this is the concentration versus distance. For the peak, this is the average of this process, we call it range. Now, if this is a Gaussian, by about 61% of the peak, this is 1 sigma. And that 1 sigma, we call it delta Rp. Delta Rp is the variance or the standard variation of the distribution. This is assuming an independent process, but this process is not independent, because when the first atom hits the surface, it amorphizes a little bit. Then the second atom amorphizes a little bit. So atom number million sees slightly different substrate. So there is a memory effect, because the more you implant, the more you cause damage. However, the profile that we measure are similar to Gaussian, so it's actually, we can implant in silicon, we can implant in photoresist, in SiO2, in silicon nitride, which are amorphous material to begin with, so actually we get a very nice Gaussian, because it's always amorphous. If the masking is the process where if I put here a thick mask, all the ions stay in the mask. They don't hit the surface. And this is an opening. I can hit the substrate and I dope the substrate. If the mask is too thin, then part of the doping will go to the substrate, and then we have insufficient mask. Now, masking is also, remember, when the ions are colliding with the substrate, they can not always move in perpendicularly. They can move also laterally. So let's assume that you have a mask, and you implant here. This is the green atoms. They are hitting the substrate, and they actually stop at a certain range, but some of them going to the side. So if the green is like the concentration of the atoms in the substrate, you form, this ion moves and stop at one place. This will move and stop in another place, but overall they will be concentrated in this region. And this is another picture of you got basically two-dimensional, the profile is two-dimensional. And we actually have a delta Rp in this dimension, and if this is the mask, you see that some of the atoms go slightly deeper under the mask. This is called sometimes lateral struggling, lateral distribution. For the same energy, let's say I shoot boron or shoot arsenic. Boron is much lighter than arsenic. So light ions go deeper. In light ions, they have more struggle. Struggle is the standard deviation. Struggle is another name for the distribution. And heavy ions do more damage because they're heavy. Now, these are actual measured profiles. This is a profile of boron in silicon implanted as, this is 30 kilo electron volt, 100, 300, 800. You can see that the profile looks with there's a long tail, and this is the Gaussian. You see that the inside edge fits very nicely a Gaussian, because inside there's much less damage. This part has slightly different distribution because there is some damage there, and there is more damage in this side. So there's some more effects. But you can see that the peak is the higher the energy, the deeper. And look at the number. At 800 kilo electron volt, it's about 1.6 micron. Now, typical implants for VLSI is 30, 20, 10, which is the range here is 0.1 micron and less. So you can implant very accurately.
Can you repeat please what is the scale?
Sorry?
What is the scale?
Okay, theoretically, this is a random process. If it's a random process, by theory, the model should be a Gaussian. This is a Gaussian. And this, the dots are actual measurements. And what you see here, that the profile of the measurement fits very nicely in this part. But here we have a very long tail. One of the reasons is that it is not a Gaussian because the process has some memory effect. The ions are heating and slowing down until they stop here. A second atom comes to slow down and stops here. And there's some slight variations. Now, in this area is damaged because of the ions. So this area, I cannot assume that the process is independent. That's why it's not a Gaussian. And some atoms slows down much more. So they don't reach this area, they stop here. While in this side of the profile, there's much less damage, so it's much closer to what you can think is a Gaussian. So this area, it's much, here you can assume more that the process is independent because there's less memory effect of the process. Again, this is kind of a little bit hand-waving in the explanation, but it makes sense. But look at another effect. If I will take the same process, this one I implant phosphorus, this is 40 kV, and this time I implant with a different doses, but here I implant exactly perpendicular to the silicon. And what I find out, that we got very nice profile for this dose. This is 1.2 10 to the 13. I increase the dose, this area disappears. You see what happens? I got one profile, but then I got like some of the electrons, some of the ions are going much deeper. While if I implant with very high dose, 7 times 10 to the 14, I don't see this. And the reason is that the reason I should have, where did I put this one? The reason is the following. The reason is that I ignored so far the fact that I'm implanting into a crystal. Now, do the following experiment. Actually, think about the following experiment. Let's say you are going into a forest, but this is not a random forest. This is an orchard. This is a place where all the trees are exactly in the same place. Now close your eyes and run into the forest. You can hit the first tree, but if you are lucky and you're running in exactly between the lines, you can run forever without hitting a tree. Slightly you will be slowed down because this is not a regular forest. You have electrons and some orbitals which will slow you down. But you can actually, if you are lucky, if the ions are lucky, they can move between the atoms and just without any collision, just propagate. This is called channeling. And lighter atoms can go deeper because this is the crystal. At some positions, if you look at the crystal, it looks like this. So if the ion hits this area, it just goes inside and can go very, very deep. If you rotate a little bit the silicon, then it will look like this. This is why typical machines today, you never implant in 90 degrees, you implant with an angle of about 7 degrees. Because you don't want this effect of channeling. This effect that ions, if they are lucky, they will go until they stop, they will be very deep. But if you shoot in an angle, you will have one collision, second collision, then you have a series of collisions, then you stop down. Let's go back to. Now, why do you see it in light dose and not in high dose? Because when you implant in a very high dose, you cause more damage to the surface. So the surface becomes amorphous. So you destroy the crystalline structure. And then you don't have this effect of channeling. Because in here, you implant with many, many atoms, so you basically destroy the structure. Now, this is I'm not going to go over this. This I gave you a table of distance versus energy for boron, phosphorus, and arsenic. This is in silicon, this is in SiO2, and this is the projected and transverse struggle. This is the range, and this is the standard variations. Now we continue. What stops the ions? The ions hit the surface and start a series of collisions. There are two types of collisions. One collision, we call it nuclear stopping, when the ion hits the nuclei. Now, the heat, you don't necessarily need a direct hit, because the nuclei is positively charged. So if the ion is going next to a nucleus, the collision can be even when there's some interaction between them, not necessarily direct collisions. If it's a direct collision or a very close hit, then the energetic ions will actually move the nucleus. If it's farther away, there will be some interaction. But if you are hitting directly, we call it nuclear stopping. And nuclear stopping causes most of the damage. Most of the damage by the ion implantation is by nuclear collisions, because when there's a nuclear collision, you actually can move the atom. But there's another mode. It's called electronic stopping. When the positive ion, there's no direct collision with the silicon. When it moves far away from the atom, and it moves inside you call it the electron orbitals of the atom, and you have some power which is formed as follows. The most common model for the effect of the electrons is what we call of the creation of a dipole. If the ion is positive and it's moving inside the structure, it attracts electrons which are actually trying to following it, because this is a positive, the ion is positive, it attracts electrons from the crystal. So you can imagine it's like a cloud of electrons going behind it. But these electrons are negative. They attract the ion, and they are coming from the lattice, and they are actually connected to the crystal lattice, and they are slowing down the electron. And you generate a retarding electric field. And so this is electronic. It's an electric field drag. It's kind of like a viscosity. So it slows down by electronic collisions, electronic scattering. The nuclear scattering is like, like in a billiard. You hit them. The most common model, by the way, that people use today for nuclear stopping is using the two balls collisions. Yes?
If the atoms that are implanted are neutral,
Yes.
we said that sometimes they are neutral, sometimes
No,
they are ionized.
as they hit the substrate, immediately they become charged. They lose. The ions, when they penetrate, they're ionized. Even if you neutralize them outside or not, they are ionized, because once they enter, they lose electrons.
In the crystal.
Because of the collision.
Oh,
Just lose a lot of electrons. And you can see here, I took it from one book, even plotted here like.
so it gets reionized by the collision.
During the collisions, basically, the definition of the ion is, or how many electrons still exist there, is very complicated, because it's a very energetic process, and you lose. And you're dealing with typical energy of the ions is like 20, 10,000 volts. You need only 15, less than even 4 electron volts to take an electron out. So practically, the atoms or ion, when it moves inside the lattice, it's an ion. Now, it's interesting that if you look at the stopping power is how much energy you lose per unit distance. How powerful is the interaction? You find out that for energy, for electronic doping, this curve is for electronic doping. For very low energy, this is ion velocity, which is in a normalized unit, but you can consider this axis as ion energy, because the kinetic energy is half mv squared. So this is energy. So for very low energy, the nuclear stopping is much, much stronger than the electronic stopping. While for high energy, the nuclear stopping is 0, while the electronic stopping is very large. And this one has fundamental result on what we do. Listen, if I shoot with high energy, how much? I give you a question. I shoot with very high energy. Let's say I'm shooting with ions in this region with very high energy. Few hundred. Typical this range is few hundred kilo electron volts. Question: do I cause any damage to the lattice? Yes or no? The question is the following. I shoot with very high energy, and I'm here. Very high electron stopping, very low nuclear stopping. Do I cause a lot of damage? No, no damage. Which means when I shoot with high energy, the surface is not amorphized, is not damaged. Only when it starts to slow down, then it's damaged. Also, if I want to cause a lot of damage, not necessarily I need to implant with high energy. Actually, the opposite. I want to implant with low energy. But what happens is the following. Let's say I shoot. This is called, by the way, the theory of the old theory of unimplantation is called the LSS theory. It was written by Linhart, Scharf, and Schott. It's a very common theory that you can find it in many, many papers, and I'm going to show you later. There is a very nice website. If you go to Google and write SRIM, or TRIM, immediately it will go to a website by Professor Ziegler, which has a very nice program that can use this theory to you can download a program that will allow you to simulate the whole ion implantation process. But this LSS theory of ionic stopping, you can assume that you have nuclear stopping and electronic stopping, and the ion goes down until they slow down. And when they slow down, they stop in a certain range, and this is the profile. you can assume that the delta E over delta X, that how much energy you lose per unit distance, is proportional to the stopping energy of the nuclei plus the stopping energy of the electrons. And this constant, SNE, or functions, are known. Once you know this, you can take it from table. People calculate it and actually confirm it by measurement. People calculated the stopping power due to nuclei and due to electron interaction. And if you have this equation, you see this is dE over dx. This is a function of E. So you transfer it from here to here, and you can calculate the range, because you take this dE over this value equal delta x. So if we integrate delta x between 0 to the range, it's the integral between 0, because when the atom stops, the energy goes to 0. So you can integrate this function between 0 to E and get the range. So this is the LSS theory. The only little thing, you need to know this function. Actually, you can solve them using quantum mechanics. First order approximation is using classical physics, but you can also do more sophisticated stuff by quantum mechanics. You can, for example, for the nuclear stopping, this is you can take the classical model that you learn in, I think even in high school, the billiard, this is not the billiard ball model. This is the actual scattering between two charged particles. This is the Rutherford model. This is also called Rutherford scattering. So this ion with an energy E1 and M1 hits the target. This ion scatters here. This ion scatters here. And then you can calculate how much energy you lose in this collision. Now let's say you have a billiard ball, and you throw at the billiard ball ping pong balls. You don't lose much energy. Also, if you take now a bowling ball and shoot on a billiard ball, you also don't lose much energy. The maximum amount of energy that you lose is when your projectile, what you shoot, the ion, and the target are about the same mass. Silicon and arsenic, they have almost the same mass. Or if I shoot silicon on silicon, I can amorphize silicon. The best way to amorphize silicon is to shoot silicon on silicon, because then the collision is the most effective. This is your delta. This is how much energy you lose versus the ratio between the mass. When the m equal 1, this is the maximum energy loss. When m equal 10, you lose only about 30%. When you go to much lower, if you are in this part, now delta E, by the way, this is, again, you have to calculate the conservation of energy and the conservation of momentum. And delta E is equal to this equation. But I would like you to understand that the most effective collision is between atoms with the same mass. Now, look what we have in microelectronics, in silicon. If I want N-type substrate, I can implant arsenic. Now, arsenic and silicon, they have the same mass. So it's a very good effective interaction. Phosphorus has different mass. So the interaction is less effective. Boron is much lighter. So it's difficult to have effective interaction with boron. This is the nuclear stopping, Coulombic scattering, assuming elastic. For example, at 100 kiloelectron volt, an ion with a mass of AMU has a velocity of about 10 to the 6 meter per second. This is 1,000 times faster than speed of sound in solids. And this is why in the solid you have phonons, or vibration of the structure. You can also generate phonons or have interaction with the phonons. So fast ion is far past nucleus before nucleus can displace in response to the Coulombic force. So nuclear scattering is not strong at high ion velocity. So if the ion is moving too fast, the amount of time it stays next to the atom is too small. So the amount of energy transfer is the interaction is effective only when you have enough time to transfer the momentum to the target. So this is why this is kind of not very accurate. You can think, what's the impulse? You remember this is from your physics days of physics 1. The impulse is the integral of power of force versus time. So if the motion is too fast, there is not enough time, you don't apply strong force and there is not much damage. Only when the atom is slow, then it goes by a long time, then you have a lot of impulse and then you have an effective interaction. This is kind of explaining why ionic nuclear scattering is effective only at low energies. Electronic energy, on the other hand, it's non-local. Basically, the faster it moves, the faster it's moved, the larger is the cloud and the larger is the stopping. This is basically, it's a non-localized phenomena. And passing ions cause internal electronic transition. Also, they can introduce ionization. By the way, these ions are very energetic. They can even generate ionization. So you can think about energy loss and small momentum transfer, and divided by the mass of, also the mass of E is very small. And because electrons can respond to fields up to very high frequency, they can respond to this velocity. The higher the velocity, the more electrons of this cloud, the more effective is the stopping. But electron stopping does not cause damage. Electron stopping only slows down the structure, the ions. So stopping power in ion implantation, you can think about it, by the way, it's, you can think about, you have stopping power. The total stopping is a combination of electronic stopping. This is like if you think only electronic stopping, high energy, it's a high, let's say I can have a structure with only electronic stopping. With only electronic stopping, at high energy it's a lot of stopping, and I plotted here with like a wide black line. And in the end of the range, it's not much electronic stopping. So the electrons are like a viscous non-local. However, when we have a transition, let's skip this one. If I have nuclear stopping, initially not much collisions, but in the end of the range, I have a lot of nuclear stopping. Now, you can think about it as at the beginning, most of the stopping is electronic, so there's no damage. Now, at the end, the ion slows down. There's a lot of damage. So most of the damage is at the bottom. Now, if we implant enough, then we can have more damage here also and here until we fully amorphize it. Now, it's interesting that we have most of the damage occurs at the end of the range. And this is one of the problems today for very shallow junction. It's called end of range damage. Because most of the damage is here, and this is where the junction is. So later when we do annealing, we have a problem here, or we can have a problem here. Okay, I'll give you some equations. This electronic stopping proportional to the square root of E. This is the total stopping, same equation as I showed you before. This is values of the total stopping. This is the values for electronic stopping. This is for light atom, heavy atoms. And I will skip this one. I'll give you some tables for the stopping function, but I will skip this down. Now, let's give you some other thing. What else you can do with ion implantation? Let's say you implant with few energies. First implant with 220 kilo electron volt, then implant with 120, then implant with 59, then with 24. What you get is the total profile will be the sum of the profiles. So you can tailor a profile. You can make a profile that goes down, profile that goes up, and it's the sum of the Gaussian. So it's very useful that you doing ion implantation, you can actually generate a profile by a sum of the ion implants. This is a result of simulation of a Monte Carlo simulation that you shoot ion after ion after ion. And this is, you implant like a delta function, and you get like a cluster of atoms being implanted. This is, I will skip again this one. This is what you get when you implant from sites. I will skip this one and go to ion implantation issues. One issue is channeling, is implanting through into a crystalline structure. Second is the damage. Third is how you activate the ions and anneal them. And last one is what we call anomalous diffusion effects. So far I assume that I implant the structure and I anneal it. And it's a one process and then a second process. But what happens is that when you anneal a structure, you change the position of the atoms. You change the position of the atoms, you change the diffusion coefficient. You change the diffusion coefficient, you change the structure again. So everything is connected together, and in the first few seconds of annealing, you can have some transient effects, or the diffusion coefficient will be different. This is the channeling which I showed you before. This is the other explanation of channeling. Let's say I shoot the ions in exact straight angle. What happens, some of them will go like this, but some will go through between the columns, and you will have one profile is the profile of the random ions, and second profile is the channeling components, the ions which are going very deep inside. This is what I showed you before. This is implanting at 0 angle. This is implanting at 2 degrees. This is implanting at 8 degrees. Sorry, this is implanting at plus 3 degrees. This is implanting at 8 degrees. And this is for a crystal of 110. What you see that when you implant at 8 degrees, it's a Gaussian. Other angles, you have much deeper, and this goes if this specific energy, I didn't write here the energy, but you can guess from the tables, and this is phosphorus with a dose of 5 times to the 12. At room temperature. What you see, the peak is about here, about less than 0.1, but the channeling can go more than 0.8 of a micron, so it's very deep. To model channeling, people use the lucky ion model, because when you shoot ions into the substrate, some of them can be lucky and channel. So there's a model called the lucky ion model. If you want to learn more, let me know. Born distribution for partial channeling, and the channeling can be partial. This is an implant at 0 degree, and in this specific, you see for phosphorus, we change the angle between 0 to 8 degrees. For boron, this is 0 degree, 0.6, and this profile is for 2 degrees. So slight changes in the angle, and this is 180 kilo electron volt, can move the range from 0.5 micron to almost 1 micron. So this is channeling effect. Channeling reduction using screen oxide. Now, how to solve this problem? Because it's a problem. We want somehow to pre-mix the ions before we shoot them. So one way to do it is to grow thin oxide on top of the silicon. Now, oxide is amorphous material. So when the ions cross the oxide, can go in every direction. So this is the profile of boron implanted at 80 kilo electron volt with a dose of 1E14 into silicon. This is at 0 degrees, so we have a significant channeling. And this is bare silicon. This is 0 degrees, and this is when we implanted 7 degrees. So in 7 degrees, there is no channeling. So this is the profile which is random. It's Gaussian, almost. And this is when you implanted 0 degrees, is this one. But if we implant through a 40 nanometer of oxide, which is 400 angstrom, the oxide is kind of a randomizer. the atoms hit it and then they go for all directions. So what you got, this is the implant at 0 degrees into silicon with oxide. We almost killed this channeling effect. And when we implanted 7 degrees, we got almost no channeling effect. The peak is slightly different. But it's very common in processing to grow thin oxide, implant through the oxide, and then remove the oxide. First, you amorphize it, and you got a better, you reduce the effect of channeling. And second one, you can, if there's some dirt, something dirty in the process, you can clean the oxide, regrow it again, and get better process. So channeling and screen oxide is what I discussed before. I will skip this slide and look at the damage. If I shoot with a very light ion, the ion moves, one collision, second, but every collision I don't lose much energy. So the amount of secondaries is very small, and the deviation from the process is not large. So the trajectory of shooting light ion looks like this. When I shoot a heavy ion, I have a lot of secondaries. And I can get basically a cluster of damage. But I want this. This is preferable. This cluster of damage is this is what I want. I want a lot of damage. I want the maximum damage. And the reason is, in order to have full annealing, I need to start with a complete amorphous material. If the material is not fully amorphous, I have an amorphous material with a polycrystalline here and a crystalline there. And when I anneal it, these little crystallines in the amorphous matrix are becoming a defect, because they are not exactly in the same orientation. So if I want good annealing, I need full amorphization. The amorphization causes defects, or the damage causes defect. And I can think about, this is a little bit material science. If you took classes of material science, I remove an atom, I have a vacancy. If I induce an atom, if I introduce an atom, I have an interstitial, or I can have a Frankel defect, which is a combination of interstitial, a vacancy in interstitial. Now, a Frankel defect, the minimum stable defect at 20 degrees is about 15 kilo electron volt. So the atom must move far enough that it doesn't go back to this structure. So I need about 15 kilo electron volt to generate this stable defect. This is what you happen in ion implantation. You hit an ion, it moves out, but if the energy is not high enough, it will go back. So you need about 4 or 5 electron volt to break a bond, but if you shoot with a 4 electron volt, the atom will go out and come back, because there's a vacancy there. But if you shoot at about 15 electron volt in silicon, the atom will go away forever, and you will generate a vacancy and an interstitial. So this is what you got. Average number of collisions or displacement that you generate is the energy of the atom that hits the substrate, and you need about 15 electron volt in every collision to cause the damage. So the amount of collisions or amount of atoms do you displace is the energy divided by 15, but this is an approximation. Usually we take 1/2. It's a much better approximation. And you can justify it by saying for high energy atom, there's more collision, less damage collision. By lower energy, you have more collision. So on average, you take a factor of 2. So this is an approximation. So the number of displaced particles per in-camera ions, it's about En, which is for example, let's take a 30 kilo electron volt arsenic ion, which has a range of 25 nanometers. And it's about 100 atomic planes. How many number of displaced particles that you have is 30,000 divided by 2/15, because 15 is the energy to generate a stable Frankel defect. And this is about 1,000 ions. And if over 100 atomic planes you displace 1,000 ions, it's a significant mixing of the atoms. So this is how it looks. you're missing about 1,000, you are displacing 1,000 atoms.
Every arsenic ion that hits displaces 1,000.
Atoms. Every arsenic atom that hits displaces, in this case, about 1,000 atoms, approximately. And this is how it looks in transmission electron microscopy. Now, what do you see here is a cross-section of silicon, and excuse me, that's not the best quality. And this is a silicon sample, ion implanted with silicon. This is very common for experiments in ion implantation, that you implant silicon into silicon. Because when you implant silicon into silicon, you eliminate the chemical effect. Because the ions of for the projectile and the substrate, they are the same. So it's only the physical effect. And what you see here, this is implant at 1E15, 1.5 E15, 2, 4, 5, 1E16 atoms per centimeter square. Now, in this structure, this is the substrate, this is the substrate, this is the substrate, and what you see here, let's go from the very high dose, 1E16. You see a very, in this specific image, this is amorphous area, and this is crystalline. But between the amorphous area and the crystalline, you see this transition region. This is the amorphous area, this is the crystalline. This is amorphous, this is crystalline, this is amorphous, this is crystalline. This is amorphous, this is crystalline, this is amorphous, this is crystalline. As you see, for high enough doses, the crystal becomes amorphous and loses all long-range order. At this point, the arrangement of the lattice atom is random, and the damage accumulation is saturated. If something is fully amorphous, you cannot amorphize it further. This is it. But it's interesting enough that you see this is amorphous area, this is crystalline. It's very impressive that the transition between amorphous and the crystalline is very sharp. And this is the beauty of ion implantation, because at the end of the range, the profile drops exponentially, like a Gaussian. It's a very sharp transition between amorphous to crystalline. So what happens next when you heat it up? This is okay. So this is okay. I skip this. I skip this picture and go here. Now, if the substrate is amorphous, and let's say that I implant, this is amorphous material. If you remember before, if I take this, this is the implanted area which is amorphous, and the substrate is crystalline. Then I heat it up. In this specific experiment, it's taken from Fletcher from the microscopy of semiconducting from 1981. And this is, if I remember well, this is an implantation by, I didn't write it here, but I think it's by silicon. Antimony, where it's written? Antimony, you're right, sorry, it's antimony. Okay, antimony is it's also one of the ions it's an N-type dopant, 6E15, 200 kiloelectron volts. So this is fully amorphous after 5 minutes. And see what happens after 10 minutes. This is crystalline, this is amorphous. The crystalline is growing by a process which is called solid phase epitaxy. This is after 15 minutes, and this is after 20 minutes. So this now amorphous area becomes thinner and thinner and thinner. But see what happens at the bottom. This is where the end of range. You see here an accumulation of defects. This is the end of range damage. So what a typical result of ion implantation, you get the amorphous layer is typically mostly annealed because of the process of solid state epitaxy. We have a regrowth of the crystalline structure. It becomes again crystalline. But now this crystalline is doped with antimony. So it's a doped semiconductor. So this region, which was amorphous, now becomes N-type silicon. This is the end of range. Here there is no much damage, but you can see, by the way, it's interesting that the end of range damage is a little bit increasing during the annealing process. And the reason is, what is damage? Damage, it's in this area, we have a transition between amorphous silicon to single crystalline silicon. We have a small number of defects. And these defects grow a little bit. We have a process of nucleation and growth of defects. Because as we know that in silicon, if we have some small defects, under some circumstances, they will disappear. But under other circumstances, they will grow because they accumulate more defects and they actually grow. So in this specific case, the end-of-range damage become more pronounced. And this is a typical process, and I guess I pick up this picture because these two effects are very pronounced. You don't necessarily always get this strong effect. Here is with antimony, which has a very significant end-of-range damage. Yes?
Is there a volume change in total in this product? Because in implant,
Yes.
other materials,
Yes.
so
Slight volume change can happen.
any problems with that? Or
Not as far as I know, as you know.
it's like,
As you know, it's a minor. But the question was, do we have some volume change? My answer was yes, a little bit, but usually what happens, you don't have a big volume change, but you generate stress. This is what you have.
go down in dimensions, you can start.
If you go to smaller dimensions, you will generate higher stress, and the stress can cause defects.
Even after the anneal, there's
Yes. No, there's no stress in the film itself. Oh, you can have some elastic stress after anneal. Yes.
Isn't the damage line depends on the surface tension? So because you have two different crystals?
No, I don't have two different crystals. This is singles. This is silicon. This is silicon.
That's not. This is doped silicon.
If this doped silicon is slightly different, maybe. I didn't think about it. Maybe you're right. Maybe because of the doped. So implant, we have defect generation, end of range damage. We have amorphization. We have the electrical activation, as I showed you before. And material defect annealing. We have the crystal defect damage. And we have this recrystallization of the amorphous layer. And we have the ion concentration redistribution. Because we hit the substrate, we can have some diffusion effects. And we also have some transient effects. I will not describe them very much here. The ion implantation damage starts near the end of range. And the damage feeds the damage, basically. Initially, it takes 15 electron volt to displace an atom, but when there is a displaced atom, then you need only 4 electron volt. So in the crystalline silicon, you need 15 electron volt to cause the damage. But once you cause the damage, you need less energy to cause another damage. So damage feeds damage. Then amorphous region first forms a depth of the ion projected range, then spreads deeper and towards the surface. Light ions may not do enough damage. Remember this. That's why junctions with boron, which is the dominant material today for P+, usually have more damage than N-type junctions, which are made by arsenic. And this is why in many processes the PMOS transistors have higher leakage current than N-type CMOS. Boron is a light atom. And light atom do not do enough damage, so they do not do complete amorphization. They can do almost complete amorphization. So during the recrystallization, we can have more damage. Because if it's not fully amorphized, we can have some crystallites of silicon inside the structure. And these crystallites are not always in the right position. Let me plot this in a better picture. But you're limited with the heat. You don't want to apply high temperature for a long time. You're limited. It's not. Let's say we have a layer, and this layer is not fully amorphized. Let's say this is amorphous silicon, and this is on silicon. And let's say it's not fully amorphized. So we have here a little crystallite. And here it's a little crystallite. And here it's a little crystallite. Then I heat the structure. what happens? Atoms start to organize themselves here and recrystallize. And typical process is that it's done layer by layer. Because once there is one layer, then the second layer, like oranges, the second layer will fit nicely in the first one. But you can also have regrowth here. Then you have a crystalline structure here, and when this crystal meets this crystal, they are not always in the same direction, and you can have some defects here. And you can see it like a point defect or kind of a gross defects inside the structure. And if this is P+, because I implanted boron, this is P+, then this area will be the junction. This will be the P+, and this is the N+. So you will have a PN junction. But because if this crystallite somehow will be close to the bottom, you can have defect which is close to the bottom, and you will have later here leakage current through this defect, and you have more leakage through the junction. In boron, which is P+, you will have more problems if you implant arsenic or phosphor, because arsenic and phosphorus are heavier and they cause more damage, then you don't have this problem.
So it's possible to first amorphize with the silicon.
Right, so how do you solve this problem? For example, implant silicon and then implant boron. This is what most of the people do today. They first amorphize the substrate and then they implant boron. And you can, typical processes today are implanting by silicon or implanting by germanium, there is another reason, which I will explain later. But it makes the process more expensive because now you have to implant twice. But I think this is what most of the people do today. First silicon, then boron, not in the same time. Look at the system. You have only single source. Now I will skip. Another interesting issue is that, as I told you before, we have about 10 to the 14, 10 to the 15 atoms per unit area. So if you think about it, if you want to amorphize the whole structure, you need about 10 to the 14, 10 to the 16 atoms to amorphize it. Like think about the raindrop model, you need about the same amount of drops per unit area that each drop will hit each atom. However, if you do this experiment and you ask yourself, what is the dose that I need to fully amorphize? And you run an experiment. For example, this is the line for bismuth. Bismuth is a heavy atom. And you find out that you run this experiment for bismuth, and you see that you can, if you do it at low temperature, this is 300 degrees, you need about less than 10 to the 14. And you heat it up to 600, you need about 10 to the 15. And the reason why at heavy temperature you need higher dose is because at higher temperature you have thermal energy, which you implant, and then you can have some annealing during the process of the implant. This is self-annealing during the implant. So in cold temperature you cause more damage, because in cold temperature, when you move an atom, it stays there. But at high temperature, you move an atom, it can go by diffusion. And see what happens. This is antimony, arsenic, and phosphorus. At room temperature, arsenic, you need about 2 times to the 14. Phosphorus, you need 10 to the 15. And look at boron. Almost impossible to do it at room temperature. So one option is to cool down the chuck. But then you need a special apparatus to do it. It's possible. People are using it. This is an interesting phenomenon that the amorphizing dose of dopant is also dependent on the temperature. I will skip this one. When the substrate is amorphous, solid phase epitaxy provides an ideal way of repairing the damage and activating the dopant, except you got some end of range damage that remain at a lower implant dose. So this is when you implant at 10 to the 14, 10 to the 15, 10 to the 16. If we implant not in 10 to the 14, if we implant in 10 to the 11, No damage at all. This is typical. So for threshold correction implants, the dose can be 10 to the 11, maybe 10 to the 12. For junctions, the dose is higher because we want to amorphize. And this is a typical process. These are typical doses. And sometimes, if you implant below 10 to the 13, then there is no damage. And then you can assume a nice Gaussian process, or you can assume a nice profile. I will summarize this lecture. I have here, this is a summary. I want to summarize, actually I'm not going to show all the slides, but I want to summarize, to use this to summarize the lecture. When you go through this implantation, you generate a profile of the implanted ions. And this is the peak. This is, by the way, plotted in a log scale. So close to the end of range, you generate a lot of damage. And the problem is you generate defects. And sometimes these defects can generate what we call a defect loops. And they're quite stable, unfortunately. So what you end up is, after your annealing, it's a beautiful area which is completely single crystal. In the end of range, you have a little bit of end of range loops. And I have a nice picture how it looks. I don't have it here, but I would like to show you now. I think this is the first time I'm showing you a real transistor. But this is a transistor. This is a transistor, a little bit an old one, not so. This is, again, I did not put the dimension, but this is an implantation technology, school 2002. This I took. This is what this is.
300 nanometers.
This is 1.28 micron. So 300. This is 300 nanometer, 0.3 micron. It's a vintage of, I would say, 1995 or 1998. So this is maybe for the Intel 486, maybe, or you know. Anyway, what you see here, this is gate. This is polysilicon. Typical on polysilicon, you have a disilicide, which I will explain later, but it's a good conductor. So this is the gate. This is the silicon. And this is the source or the drain. This is the source of the drain. But what you see here, the drain is actually made by disilicide, and this is the silicon junction. And this is the junction here, also the same junction. And these junctions are made by ion implantation. By the way, if you look at the structure of the device, this is the poly gate, and this is the junctions, and between the poly gate and the junction we have a spacer. Now, if some of you took my class on advanced semiconductor devices, let me remind you, why do you need the spacer? In modern devices, the transistor, the junction here is heavily doped. Here it's difficult to see, this area is lightly doped. So this structure is called a lightly doped drain, or LDD. And the reason you put the source and the drain is a little far away from the heavily doping, the heavily doped, you put slightly far away from the transistors. So if you do the modeling here at the corner, you have less electric field. If the junction was here, you have higher electric field. So by moving a little bit away the junctions and put here lower doping, you have lower electric field here. And because you have lower electric field, you have less hot electrons. And because you have less hot electrons, you have much better reliability. Now the reason I put here polysilicon, this is the gate it's conducting, but to improve the conductivity of the polysilicon, we put here a material which is called disilicide, or titanium silicide, which is about factor of 100 more conducting than polysilicon. This is reduce the gate resistivity, because gate delay is R times C. So if you reduce R, you improve gate delay and you make the circuits much faster. And this is done by ion implantation and later on by silicidation, which we will discuss when we talk about junctions. So I skip this high dose annealing stage, and we summarize this lecture. Ion implantation provides great flexibility and excellent control, and we can control the ion energy. We have damage accumulate with the implanted dose and may amorphize the substrate. And the open structure of the silicon lattice leads to ion channeling. And I did not discuss transient enhanced diffusion. We'll discuss it about tunneling. One last thing before we go. I want to show you. If you go, I hope I have internet here. And if you Google, sorry. And you put SRIM. Somebody here, somebody was before with this. You go to this website. I'm not doing the whole process, but here you have a nice textbook on ion implantation. This website is basically particle interaction with matter. Wow, cool. Who the students who built this website were? I want you to do it in my website. Where are my students? Nice. You have a SRIM, the stopping and range of ion in matter, and ion beam analysis. And then you have the source. You have two programs, SRIM and TRIM. TRIM is the old program, just give you the range. SRIM is more sophisticated, newer program, and you can download it. It's free. And you have some historical review. It's a very nice if you're interested in ion implantation and you have nothing to do. I know that you are very busy fellows, but if you really want to learn about ion implantation, this is the website. This software is very easy to install on any PC. So I installed it. You can download, and you can download SRIM and TRIM. I think TRIM is part of TRIM. So then you have all this information about it and explanation and everything. So if you want to solve some problems, this is the site. And I think Asya in the exercise will use this program to show you give you some explanation. So we finish ion implantation. Next week, Monday, we start to study junctions.